All right, so in this video, we finished section 7.5 and run through section 7.6, which will complete chapter 7. This first example is sort of the details from the R example that we worked on last time. So why don't you pause, copy, and play. All right, so we're looking at the arsenic levels in Bangladeshi wells, and we're constructing a bootstrap T confidence interval. We had 271 wells. Our original sample, those 271 wells, had a sample average of 125.32 parts per billion of arsenic and a standard deviation of basically 298. We did 10 to the fourth resamples, and we constructed a bootstrap distribution of that T statistic. The 2.5% quantile was at negative 2.643. I think mine was negative 2.66 something or whatever, but whatever. And the 97.5% quantile was at 1.685. And thus, we were able to construct our bootstrap confidence interval by taking sample mean minus Q2 times S over root N, and then sample mean plus Q1 times S over root N, and that ground out to 95.78 and 173.18. So if we had 100 different samples, each containing data from 271 wells in Bangladesh, and with each of these 100 samples of 271 wells, we constructed confidence interval, then 95% of the time, the population average amount of arsenic in any well in Bangladesh would be within the confidence intervals constructed, okay? So we could say we're 95% bootstrap confident that the population mean of average arsenic level of wells in Bangladesh is between 96 and 173 parts per billion, okay? All right, now, if you recall, the arsenic data was way not symmetric. So if we had used the technique from section 7.1, the second technique where we used the T distribution itself, which assumed symmetry, if we had used that technique on this data, then our confidence interval would have been from 90 to 160. And as you see, that certainly shifted left from what our bootstrap T confidence interval is. And that makes some sense because if you recall our arsenic data, it was really right-tailed, so it was skewed right, and the T distribution is not picking up on that skewness, but the bootstrap distribution is. Okay. All right. So take home is that for non-symmetric populations, the bootstrap T confidence interval is the most accurate confidence interval we have in general. Okay. All right. So one variant of a bootstrap T distribution is the difference of means. So why don't you pause, copy, and then press play. So now let's say we had two populations and we grabbed a sample from each one, and we want to examine the difference in the population means, mu1 minus mu2. What we're going to do is we're going to resample each of the data sets we're given, each of the original two samples, and calculate this bootstrap T statistic for each resample. So T star will be the resample mean of the first sample minus the resample mean of the second sample minus the original first sample mean minus second sample mean all over this square root where S1 star and S2 star are the standard errors for the resamples, okay? So we calculate that T statistic 10 to the fourth or 10 to the fifth times and generate a distribution for it. I shouldn't do symmetric, it might not be symmetric. And then if we look, and we're going to grab the alpha over 2 and 1 minus alpha over 2, so like 2.5 and the 97.5% quantiles of that distribution, that empirical distribution, then we got this lovely formula for the bootstrap T confidence interval. Difference of the original sample means minus the second quantile plus the first quantile times that square root, where the S1 and the S2 are from the original sample, okay? All right, so again, we're not going to have to memorize this. We're going to have a note card. We can write it down on it, but the form of it should be feeling vaguely familiar and relatable based on what we've done. All right, so that's the end of section 7.5, and 7.6 is sort of more of a comparison of what we've learned, okay? Okay, so in chapter 7, In chapter 7, we've been looking at confidence intervals, and we started by what happens if we had a normal population where we know the standard deviation of the variance. That was 1. Section 7.1, the first guy. What happens if we have a normal population where we don't know the variance? And that's where we introduced the t distribution, which we then said we can actually use this even if the population is not normal but is symmetric. Okay. And then we asked, well, what happens if our population or on our data doesn't look symmetric? Well, then we introduced the bootstrap t confidence interval to try and handle that. And that was section 7.5. Okay. So on this panel, we're going to compare a t confidence interval. So that would be section 7.1, method 2, with the bootstrap t confidence interval. That's section 7.5. Okay. So why don't you pause, copy, play. All right, so this is section 7.6, and we're basically going to illustrate that we can start to compare these two different methods of creating confidence intervals, but there's a lot of work still needs to be done by statistical researchers, okay? So first off, confidence interval accuracy. By definition, a 95% confidence interval should include the actual population parameter we're interested in, which has often been mu, 95% of the time. And it should miss 2.5% on each side. So 2.5% of the confidence intervals should have the population mean to the left of it, and 2.5% of the confidence interval should have the population mean to the right of it, right? So that's the ideal of what a confidence interval should be, at least 95% confidence interval. Okay, well, t confidence intervals are first order accurate. That means they converge to this ideal as our sample size approaches infinity. So the bigger the sample size, the better you get. But it converges slowly. Like imagine how quickly it takes for c over the square root of n to go to 0 as n gets bigger, okay? Somewhat slowly. Now a bootstrap t confidence interval are second order accurate. They also converge to this ideal, but much faster. So imagine how much faster c over n converges to 0 as n approaches infinity versus c over the square root of n, okay? So chalk 1 up for bootstrap t. Lengths. Ideally, our confidence intervals aren't too wide or aren't too long, right? We want to sort of narrow band for where we think this population parameter should lie, okay? Well, the t confidence interval pays a length penalty for estimating the variance or the standard deviation. So remember, we used a t confidence interval when we didn't know the variance of the normal distribution that we're dealing with, okay? And so we estimated it. Well, the bootstrap t confidence interval pays that same penalty, plus it pays a penalty for handling the skewness correctly. Because remember, we use bootstrap t when the data doesn't look symmetric, it's skewed. And we pay another penalty for estimating the actual skew of the data. So bootstrap t confidence intervals tend to be a bit wider than t confidence intervals because of skewness. This is one we don't get into too much, but it's an interesting mathematical one to ponder. We would love confidence intervals to be transformation invariant. So what this means is, let's say there's two population parameters, sigma and theta. And let's say they're related via a function, h of theta equals sigma. We've seen this, like an exponential distribution, the variance is equal to the mean squared. Or is that a Poisson? One of those. The variance is equal to the mean squared. So the variance is a function of the mean. So ideally, if I could get a confidence interval for the mean, can I transform that into a confidence interval for the variance? That's the hope, right? And we write that by saying, look, there's the left end of the confidence interval for theta. Let's give it to the function. Will it give me the left end for the confidence interval for sigma? That'd be nice. I don't know if that's sigma or not, but whatever that symbol is. And similarly, can I take the right end of the confidence interval for theta, and the function will map it over to the right end, the upper bound of the confidence interval for sigma? That'd be awesome. The t confidence interval is not transformation invariant. No, not happening. The bootstrap t confidence interval is almost transformation invariant, and we sort of have seen some hints about that. Like in chapter 5, the bootstrap percentile intervals were transformation invariant. So we saw hints that the bootstrap behaves well under a function mapping into another parameter description. Okay, not too important to focus on. All right, and then last but not least, to finish off chapter 7, ease of use. Bootstrap T confidence intervals are computationally expensive to build, right? Now, it doesn't seem that way in our class because we're looking at relatively small data sets. But if you have a large data set and you're trying to do a bootstrap simulation of it, it can really clog up even a really strong and powerful computer or parallel computers, okay? So Bootstrap T confidence intervals, you pay a computational price to construct them, all right? And it's a significant price for a lot of data sets, right? So all this is to say there's a lot of ongoing research here trying to find better ways of creating better confidence intervals, right? So go to grad school, get a stat PhD, come back to St. Thomas, teach, do some interesting research.